Hello everyone, it's Mr. Dunbar here. This is 14.3, the Compton Effect. I'm assuming that you've watched these other couple of little videos. However, I just want to explain a little bit about what the Compton Effect actually is. Now, basically what you've got is a photon that'll be coming in and hitting an electron that's usually in orbit. Now, as the photon comes in, this electron is going to wind up shooting off in this direction, and you see the photon coming along this way, usually with a longer wavelength. And essentially what happens is that this collision of a photon, something that is just electromagnetic radiation, and this electron, something that is matter, they collide and interact with one another as if they were both objects. And essentially, we've got the law of conservation of momentum actually acting in place here. Now, a couple of formulas that are on your formula sheet. The first one is E is equal to P times C, and the second one, right, energy is equal to the momentum times the speed of light. So this is momentum of a photon, energy of a photon, and speed of light, the speed of a photon. Next thing we're going to have is P is equal to h over the wavelength. And this is, again, the momentum, Planck's constant, divided by the wavelength. Now, these two formulas, they are on your formula sheet. Right, so this one and this one you can find on your formula sheet. But if we think about this in terms of V is equal to wavelength times the frequency, or the velocity divided by the frequency is equal to the wavelength, and substitute this in here, you actually wind up with this equation, which is P equals hf over V. And if you really start to think about this, this is actually just a manipulation of the first formula, dividing both sides by C, and energy just being hf, or the energy of a photon, which we had talked about earlier. So those are formulas. Let's take a look at a couple of examples. All right, so taking a look here, calculate the momentum of a photon with the wavelength 625 nanometers. So P is equal to h over lambda again. We're looking for the momentum. H, now we're going to use 6.63 times 10 to the negative 34 joule seconds. And we're going to divide that by 6.25 times 10 to the negative 7 meters. So when you calculate that out, you wind up with 1.06 times 10 to the negative 25 joule seconds per meter. Now, a joule, unit of work, is a Newton meter. So the units here wind up actually being Newton meters per second, Newton meter seconds per meter. And you notice the meters cancel out, and you're left with units of Newton seconds, which is a unit that we've constantly used, that we've used for momentum in the past. Now, a Newton being a kilogram meter per second squared multiplied by seconds, and again we can see here the second, one of the seconds cancels, and you're left with kilogram meters per second, which is also a unit that we've used for momentum. So this is just another way of expressing the same thing with each one of those. Let's take a look at the So taking a look at this next one, E is equal to PC. We've been given the momentum. We're actually looking for the frequency, so we're going to substitute in HF, energy of the photon, for E, and we'll divide both sides by Planck's constant. E is equal to PC over Planck's constant, where, oh sorry, that should be frequency. So we're looking for the frequency. The momentum has been given to us, 2.80 times 10 to the negative 27. C is 3 times 10 to the 8. And we're going to divide that by Planck's constant. We'll use 6.63 times 10 to the negative 34 joule seconds. We'll keep everything in standard units here. And so frequency with this becomes 1.27 times 10 to the 15 hertz. So taking a look at this next one here, we've got calculated momentum of a 660 kilo electron volt photon. So this is a unit of energy. We're looking for the momentum, and so again we're going to use E is equal to P times C, dividing both sides by C. So we're going to use E over C is equal to momentum. So 660,000 electron volts divided by 3 times 10 to the 8 meters per second will be equal to the momentum. So the momentum here, when you calculate this out, gets you 2.2 times 10 to the negative 3 electron volt seconds per meter. Now, if we wanted this in joule seconds per meter, get it to standard units. Now, converting electron volts to joules would be multiplying by 1.6 times 10 to the negative 19 joules per electron volt. And so we're actually going to just do that with this, joules per electron volt. Notice that in this case here, the electron volts cancels out, and you're going to get your answer in joule seconds per meter. And so this winds up being a 3.52 times 10 to the negative 22 joule seconds per meter. And we've already established up here that that is the same as a Newton second or a kilogram meter per second. So that is your standard unit. I would like you to try this next one. So pause the video, give this next one a try, and then we'll come back to it in a moment. Okay, so coming back to this, taking a look here, momentum is h divided by wavelength, or wavelength is equal to h divided by p. Put in your numbers, you should have wound up with 1.1 times 10 to the negative 13 meters. Finding the energy, that's P times C. We've got the momentum multiplied by the speed of light. You should have wound up with 1.8 times 10 to the negative 12 joules. Now, I just realized that I did this to 2 significant digits. The question was a 3-digit question. Hopefully that's not going to throw anybody too much for a loop. Anyway, that's it for part 1. Actually, we'll do one more. We'll do one more before we move on to part number 2. Just let's take a look at this concept. Check pretty questions. Which of the following photons has a greater momentum? One with 500 nanometers, wavelength 500, or 2 nanometers? And explain your reasoning. Well, if momentum is equal to h over wavelength, which one will generate a greater momentum? Put your thoughts in. Okay, you got it? Okay, well, the greater this number here, the greater the wavelength, the smaller this value is going to be overall, which means the smaller the momentum. So if this is greater, this will be smaller. So by the same logic, if this is smaller, then this momentum will be greater. So if smaller wavelengths is greater, the one that is a smaller wavelength is the 2 nanometers. Okay, let's move on. Move on to part 2 of this video.